Have you ever wondered what happens when something in space simply opens its eyes after sleeping for decades? In 2019, astronomers watched in real time as Sagittarius A, the supermassive black hole at our galaxy's center, suddenly flared to 75 times its normal brightness in just 2 hours. Dr. Tuan Do at UCLA, who captured the event, couldn't believe what he was seeing. This wasn't supposed to happen. The monster we thought was dormant had just revealed it was wide awake. For 25 years, we'd been monitoring Sgr A with every telescope we had, and it seemed relatively calm. That May evening in 2019 shattered every assumption. The black hole exploded into activity with an intensity we'd never witnessed, then dropped back to normal as if nothing had happened. No warning, no explanation. Just raw, terrifying power on display for 2 hours before vanishing again. But here's what keeps astronomers awake at night. That flare wasn't unusual behavior for Sagittarius A. It was normal behavior we'd simply never seen before. Tonight, we're exploring the 10 specific ways this 4 million solar mass black hole threatens everything around it, and why this sleeping giant might be far more dangerous than we ever imagined. Now let's begin. Chapter 1. Hidden Monster. The center of our galaxy should be visible from Earth. It should dominate our night sky, a brilliant concentration of hundreds of billions of stars compressed into a relatively small region of space. But when you look toward the constellation Sagittarius, you see almost nothing. Dust clouds spanning thousands of light years obscure our view, hiding the galactic core behind cosmic curtains that block visible light almost completely. For most of human history, we had no idea what lurked there. We couldn't have known that the darkness concealed one of nature's most destructive forces. Sagittarius, AI itself, is invisible by definition. A black hole with an event horizon so absolute that nothing, not even light, can escape once it crosses that boundary. But the region immediately around it blazes with activity. The accretion disk, a swirling mass of superheated matter spiraling toward destruction, glows with temperatures exceeding 10 million degrees Celsius. Jets of charged particles shoot outward along the black hole's rotational axis at nearly light speed. And the gravitational forces in this region are so intense that stars orbit the central darkness at speeds exceeding 5,000 kilometers per second, more than 1% the speed of light. To put that velocity in perspective, imagine Earth orbiting the Sun at such speed that it completed a full year in less than 3 hours. That's the environment surrounding Sgr A. Stars that would take millions of years to complete an orbit around a normal galactic center whip around this monster in just 15 years. The star, designated S2, which astronomers have tracked since 1995, comes within just 17 light hours of the event horizon at its closest approach, about 4 times the distance from the Sun to Neptune. At that proximity, it experiences gravitational acceleration strong enough to visibly stretch the light it emits, a phenomenon called gravitational redshift that Einstein predicted but seemed too extreme to ever observe directly, until we observed it happening around Sagittarius A. The black hole itself measures roughly 44 million kilometers across, about the distance from the Sun to Mercury. But don't let that modest size fool you. Packed into that volume is approximately 415 million times the mass of our Sun. The density defies comprehension. Every cubic centimeter at the event horizon contains more mass than our entire solar system, and that's just the boundary. What lies beyond the event horizon, in the region where space-time curvature becomes infinite, remains literally unknowable. Information cannot escape to tell us what happens there. Reinhard Genzel and Andrea Ghez shared the 2020 Nobel Prize in Physics for their decades-long work mapping the orbits of stars around Sgr A, proving beyond doubt that a supermassive black hole occupied the galactic center. Their observations revealed something crucial. The stars weren't just orbiting empty space. They were orbiting something compact, dark, and so massive that no other explanation fit the data. By tracking stellar positions with precision better than tracking a golf ball on the moon from Earth, they demonstrated that more than 4 million solar masses occupied a region smaller than Mercury's orbit. Only a black hole could be that dense. But here's what makes Sagittarius A particularly fascinating from a danger perspective. It's currently underfed. The material it's actively consuming right now amounts to only about 1,000th of a solar mass per year. That might sound like a lot, and it is objectively, but for a black hole of this size, it's almost nothing. M87 by comparison, consumes matter at rates thousands of times higher. Sgr A FAS is operating at a tiny fraction of its theoretical maximum, feeding on sparse gas and the occasional unlucky star that wanders too close. This creates a deceptive sense of safety. We see it relatively quiet with only occasional flares and outbursts, and we assume it's always been this way. We assume it will remain this way, but the evidence tells a different story. Radio observations reveal massive bubble structures extending thousands of light years above and below the galactic plane, remnants of explosive events that occurred millions of years ago. X-ray telescopes detect echoes of past feeding frenzies, light from ancient outbursts reflecting off distant gas clouds and reaching us millennia after the events themselves. Sgr A might seem quiet today, but it has a violent past, and that past suggests an even more violent potential future. Consider what happens when a star ventures too close. Not into the black hole itself, but merely into the region where tidal forces become extreme. Gravity pulls on the near side of the star far more strongly than the far side. The star stretches, elongates, and eventually tears apart in a process called spaghettification. The stellar material doesn't simply fall in, it forms an accretion disk, friction heating it to millions of degrees. This superheated material emits X-rays and gamma rays powerful enough to sterilize any planets within light years. The process releases more energy in hours than our sun emits in centuries, and this isn't hypothetical. In 2018, astronomers observed a mysterious object designated G2, a cloud of gas and dust, making a close approach to Sgr A. Predictions suggested it would be torn apart and consumed, possibly triggering a massive outburst. Instead, G2 survived, leading scientists to suspect it might be a star shrouded in gas. But the encounter demonstrated that Sgr A actively disrupts objects passing near it. The question isn't whether it destroys things. The question is what happens when it destroys something much larger than a gas cloud. The magnetic fields around Sagittarius A deserve special attention. Measurements from the Event Horizon Telescope collaboration revealed field strengths approaching 1 trillion times Earth's magnetic field. These fields don't just exist, they actively channel matter into jets, accelerate particles to relativistic speeds, and shape the flow of material near the event horizon. When matter falls toward the black hole, these magnetic fields can redirect it, flinging it outward in collimated beams that stretch for thousands of light years. This isn't gentle, this is violent, explosive, and ongoing. You might wonder why any of this matters. Sgr A sits 26,000 light-years away, a distance so vast that light from events happening there right now won't reach Earth until the year 2825 AD. Surely we're safe at such cosmic remove. But remember, we're not talking about isolated events, we're talking about an object that fundamentally shapes our galaxy structure, that influences stellar orbits throughout the galactic core, and that has periodically unleashed energy on scales that affect the entire Milky Way. The danger isn't that Sgr A will reach out and grab Earth. The danger is what happens to galactic environments when such monsters feed, and what that means for the long-term habitability of regions surrounding them. As you go about your day, remember that you are orbiting this object. Every second, the Sun carries you at 230 kilometers per second in a vast orbit around the galactic center. That orbit takes 230 million years to complete, and at the center of that orbit, providing the gravitational anchor for our entire journey through space, sits Sagittarius A. Quiet now, but harboring potentials for destruction that dwarf anything else in our cosmic neighborhood. We've identified what Sgr A is, a 4 million solar mass black hole operating at the center of everything we know. But identifying it and understanding its true nature are different things, because the evidence suggests this monster has a history far more violent than its current quiet state implies, and that history reveals just how dangerous it can actually be. Chapter 2. Violent past. In 2010, NASA's Fermi Gamma-ray Space Telescope detected something extraordinary. 2 enormous bubbles of high-energy radiation extending 25,000 light-years above and below the galactic plane. These structures, now called the Fermi Bubbles, represent the largest known features emanating from the Milky Way's center. They dwarf individual star clusters, rival the scale of galactic spiral arms, and contain enough energy to power 1 trillion stars for 1 million years. And they came from Sagittarius A. The implications stunned the astronomical community. These bubbles don't form from gentle processes. They form from cataclysmic explosions, from matter being ejected at velocities approaching the speed of light, from energy releases so profound that they reshape galactic structure across thousands of light-years. The estimated age of the Fermi Bubbles ranges between 6 and 9 million years, recent in cosmic terms, nearly contemporary with early human ancestors. Sgr A was violently active within Earth's recent geological past. But here's what makes this revelation particularly disturbing. The Fermi Bubbles represent just one event. Astronomers have since discovered multiple lines of evidence suggesting that Sagittarius A undergoes periodic outbursts, feeding frenzies that temporarily transform it from a quiet monster into an active galactic nucleus, the most luminous category of object in the universe. Radio observations reveal older structures, fainter and more dispersed than the Fermi Bubbles, suggesting previous explosions reaching even further back in time. X-ray echoes bouncing off molecular clouds show that Sgr A was at least 1 million times brighter just 300 years ago than it is today. Think about that timeline. In 1724, as Bach composed his St. John Passion, and Newton's theories dominated scientific thought, Sagittarius A was unleashing X-ray radiation powerful enough that we're still detecting reflections of it nearly 3 centuries later. The light we see now bouncing off clouds thousands of light-years from the galactic center is merely an echo of that ancient outburst. And it wasn't even a major event by the black hole standards, just a larger-than-usual feeding episode, probably from a star or gas cloud that wandered too close. Dr. Gabriele Ponti and colleagues at the Max Planck Institute for Extraterrestrial Physics have mapped these X-ray echoes in remarkable detail. They reveal that Sgr A's luminosity varies by factors of millions over timescales of decades to centuries. The black hole doesn't feed steadily, it pulses, flares, and occasionally explodes into periods of extraordinary activity. During these outbursts, the radiation output doesn't just increase, it transforms the entire galactic center environment. Molecular clouds light up with reflected X-rays. The thin gas filling the space between stars becomes ionized across volumes spanning hundreds of light years. And any planets or life-bearing worlds in those regions face sterilizing doses of high-energy radiation. The mechanism behind these outbursts relates directly to what Sgr A consumes. Most of the time, it feeds on thin gas slowly spiraling inward from the interstellar medium. This produces the relatively quiet state we observe today. But occasionally, something massive falls in. A star ventures too close and gets torn apart. A dense gas cloud loses orbital energy and plunges toward the event horizon. When this happens, the sudden influx of material can't be processed smoothly. The accretion disk becomes overfed, unstable, and prone to explosive ejections. Matter that should have been consumed gets flung outward instead, carrying enormous energy with it. Simulations by astrophysicist Elena Merchikova at the Institute for Advanced Study suggest that Sgr A experiences major feeding events roughly every 10,000 to 100,000 years, with truly catastrophic outbursts perhaps every few million years. These aren't precise predictions. The chaotic nature of gas dynamics and stellar interactions makes exact timing impossible. But the pattern is clear. Sgr A operates in cycles. Quiet periods, like the current era, alternate with active periods. When the black hole's luminosity increases by factors of thousands or millions, we happen to be living in a quiet phase. We happen to be observing it during an unusually dormant period. But the evidence scattered throughout the galactic center proves this dormancy is temporary. Consider the fate of any civilization existing within 1,000 light-years of Sgr A during one of these outbursts. The radiation levels would be extraordinary, not just higher than Earth's background radiation, millions of times higher. High-energy X-rays and gamma rays would penetrate atmospheres, destroy ozone layers, and deliver lethal doses to any exposed life. There's no hiding from it, no shielding that would protect surface environments. Planets in the galactic center aren't just exposed to occasional supernovae or gamma-ray bursts from distant sources. They're exposed to a permanent, massive radiation source that periodically increases its output to levels that make survival impossible. This creates a fascinating and disturbing implication. The galactic center might be fundamentally uninhabitable over cosmic timescales. Even during quiet periods, the radiation environment exceeds anything in the outer galaxy by orders of magnitude. During active periods, it becomes completely lethal. Any life that evolved there would face periodic extinction. Events not from asteroid impacts or volcanic eruptions, but from the central black hole simply feeding. The cycle would be inevitable, inescapable, and ultimately unsurvivable. We're fortunate in this context to inhabit a region 26,000 light-years from the galactic center. That distance provides a buffer. The radiation from Sgr A's outbursts attenuates over such vast reaches, spreading its energy across cubic light-years, so enormous that the intensity drops to negligible levels by the time it reaches Earth's neighborhood. We see the echoes of past violence, but we don't experience the violence itself. The black hole's danger doesn't extend to the outer galaxy in any immediate sense. But imagine being closer. Imagine being one of the stars in the S cluster, the collection of young, massive stars orbiting within light weeks of the event horizon. These stars exist in an environment where Sgr A's radiation dominates everything. When the black hole flares, these stars are bathed in high-energy photons powerful enough to strip away stellar atmospheres. The young age of S-cluster stars, most, are less than 10 million years old, suggests they formed relatively recently from gas that accumulated near the black hole. They're survivors, in a sense, existing in a region that periodically becomes hostile to the very processes that created them. Dr. Andrea Ghe's team has documented curious properties of these S-cluster stars. Many show unusual chemical compositions, signs of mass loss, and orbital perturbation suggesting they've experienced close encounters with the black hole or its accretion environment. Some might be the survivors of binary systems where the companion star was consumed by Sgr A. Others might be the remnants of larger stars that lost significant mass to tidal stripping. Each one tells a story of survival in the universe's most hostile neighborhood, survival that might be temporary, measured in cosmic terms. The historical record preserved in the galactic center paints a clear picture. Sagittarius A is not and has never been a passive object. It's an active, violent, periodic threat that shapes its environment through episodes of extraordinary energy release. The current quiet period is an aberration, a temporary lull in a pattern of violence extending back billions of years. And the evidence suggests that these violent periods can begin suddenly, triggered by events as simple as a single star wandering off course. You're observing this object during one of its calmest phases. The radiation you would receive if you stood on an imaginary planet near the galactic center right now is merely extreme, not instantly lethal. But that baseline can change with little warning. A gas cloud falls in, the accretion rate spikes, and suddenly the radiation environment multiplies 1,000-fold. This isn't science fiction. This is documented behavior of the object sitting at our galaxy's heart. The violent past of Sagittarius A isn't ancient history confined to billions of years ago. It's recent, ongoing, and cyclical. The Fermi Bubbles prove that major outbursts occurred within the last 10 million years. The X-ray echoes prove that significant flares happened within the last few centuries, and the physics governing the system guarantees that future outbursts are inevitable. The only questions are when and how severe. So we've established what Sgr A has done. Now we need to understand what it's doing, the invisible dangers that exist even during these supposedly quiet periods. Because the violence doesn't stop. When the black hole isn't actively feeding, it just becomes harder to see. Chapter 3: Radiation Prison. If you could somehow survive the journey to within a few light years of Sagittarius A, you'd encounter something invisible but absolutely lethal. A permanent radiation field so intense that it would kill you in seconds. Not minutes, not hours, seconds. This radiation doesn't come from the black hole itself. Remember, nothing escapes the event horizon. It comes from the processes happening just outside that boundary, from matter being torn apart at molecular and atomic levels, from particles being accelerated to velocities where physics becomes relativistic and deadly. The zone immediately surrounding Sgr A is bathed in X-rays with energies measured in kiloelectron volts, thousands of times more energetic than visible light photons. At distances of just a few light days from the event horizon, the X-ray flux exceeds Earth's entire radiation environment by factors of billions. A human body exposed to this environment wouldn't just develop radiation sickness. The cellular damage would be instantaneous and absolute. DNA molecules would shatter, proteins would denature. The biochemistry of life would simply cease to function. But X-rays represent just one component of the radiation environment. The region around Sgr A also generates copious gamma rays, photons so energetic that each one carries more momentum than a pitched baseball. These aren't just dangerous to living tissue, they're dangerous to matter itself. When a gamma ray photon with sufficient energy strikes an atomic nucleus, it can trigger nuclear reactions, transmuting elements and generating cascades of secondary particles. The space near Sagittarius A is so flooded with gamma radiation that ordinary matter would undergo continuous nuclear bombardment, gradually transforming and degrading at the atomic level. Then there's the particle radiation. Charged particles, primarily protons and electrons, accelerated by Sgr A's magnetic fields to velocities approaching light speed. These relativistic particles carry kinetic energies that dwarf anything we can produce in particle accelerators on Earth. When they strike, Matter, they don't just penetrate it. They can trigger particle showers where a single high-energy proton hits a nucleus and generates dozens or hundreds of secondary particles. Each of those secondary particles carries enough energy to cause additional damage. The result is a cascade of destruction from a single particle impact. Dr. Frederick Baganoff at MIT, studying the X-ray emission from the Galactic Center with the Chandra X-ray Observatory, discovered that the radiation environment around Sgr A fluctuates dramatically on timescales of minutes. The black hole doesn't emit steadily. It flares, sometimes increasing its X-ray output by factors of 10 or more in less than an hour, then declining just as rapidly. These flares aren't predictable. They don't follow regular patterns. They simply happen, driven by chaotic processes in the accretion flow that remain poorly understood. Imagine living on a planet in that environment, if such a thing were possible. You'd experience unpredictable radiation storms that could arrive with minutes of warning. One moment, the background. Radiation is merely extremely high. The next moment it's multiplied tenfold and anything on the surface faces lethal exposure. There's no advance notice, no way to predict when the next flare will occur. You'd live in a state of permanent danger from an enemy you can't see, hear, or feel until it's already killing you. The magnetic fields that dominate the region near Sgr A create additional dangers beyond direct radiation exposure. These fields are so powerful, again, roughly 1 trillion times Earth's magnetic field at their strongest, that they affect the motion of charged particles in ways that concentrate radiation into specific zones. Think of them as cosmic lenses that focus deadly radiation the way magnifying glasses focus sunlight. Regions that should be relatively safe based on distance alone become death traps because magnetic field lines funnel high-energy particles directly through them. Observations from the Event Horizon Telescope collaboration revealed these magnetic field structures in unprecedented detail. The radio emission from around Sgr A shows clear signs of synchrotron radiation, light emitted by electrons spiraling around magnetic field lines at relativistic speeds. The pattern of this emission maps the geometry of the fields themselves, and what that geometry reveals is disturbing. There are regions where the field lines converge, creating zones of concentrated particle density and correspondingly intense radiation. These zones shift and change as the accretion flow evolves, creating an environment where safe areas can become lethal with little warning. To put the radiation levels in perspective, consider that Earth's surface receives roughly 0.3 microsieverts of cosmic radiation per hour, mostly from the Sun and distant cosmic ray sources. An unshielded astronaut in Earth orbit receives about 80 microsieverts per hour. The interior of the Chernobyl reactor core immediately after the disaster emitted roughly 300 sieverts per hour, 1 million times higher than Earth's surface, lethal within minutes. Now consider this: the radiation field just a few light days from Sgr A exceeds the Chernobyl core by factors of millions. We're talking about radiation environments where the concept of lethal dose becomes meaningless because any exposure whatsoever is instantly fatal. And this is during the quiet period. When Sgr A actively feeds on a star or large gas cloud, the radiation output increases proportionally. The X-ray luminosity can jump by factors of thousands. The particle acceleration intensifies. The magnetic fields become even more twisted and complex. The zone of lethality expands outward, potentially reaching distances of dozens or hundreds of light years, depending on the severity of the outburst. During major feeding events, the galactic center becomes a radiation furnace that would sterilize planets across volumes comparable to the space between the Sun and Alpha Centauri. You might think that shielding could protect against this radiation. After all, we shield spacecraft against solar radiation, and nuclear reactors use thick concrete and lead to contain their emissions. But the scale of shielding required to protect against the galactic center radiation environment would be absurd. Lead shielding effective against medical X-rays is measured in millimeters. Shielding against the X-rays near Sgr A would need to be measured in meters, solid meters of dense material. And that's just for X-rays. The gamma rays would require even thicker shielding. The high-energy particles would penetrate anything short of entire mountainsides of rock. Dr. Daryl Haggard at McGill University, analyzing the multi-wavelength emission from Sgr A, discovered that the black hole's radiation output extends across the entire electromagnetic spectrum simultaneously. It's not just emitting X-rays or just emitting radio waves, it's emitting everything from low-frequency radio through visible light, ultraviolet, X-rays, and into the gamma-ray regime all at once. This means there's no safe part of the spectrum to work with, no wavelength band where the radiation is manageable. Every frequency carries lethal energy levels. The implications for exploration are devastating. We often imagine that future civilizations might travel to the galactic center to study Sagittarius A up close, perhaps establishing research stations in orbit around the black hole at what we consider safe distances. But the radiation environment makes this effectively impossible with any technology we can currently envision. You can't simply arrive at the galactic center with conventional spacecraft and expect to survive. The radiation would destroy electronics, break down materials, and deliver lethal doses to any crew within hours of entering the region, even at distances of multiple light-years from the black hole itself. This creates a fundamental barrier to understanding Sgr A through direct observation. We can observe it from Earth, 26,000 light-years distant, where the radiation has attenuated to negligible levels. We can send signals through the intervening space and reconstruct what we detect. But we cannot go there. Not with current technology, and possibly not with any technology that operates on principles we currently understand. The radiation prison around Sagittarius A is impenetrable, and yet, remarkably, matter does reach the black hole. Gas and dust spiral inward through this radiation environment, somehow surviving long enough to cross the event horizon. The mechanism by which this happens remains only partially understood, but it likely involves magnetic fields that channel the material along specific trajectories, shielding it from the worst of the radiation through a combination of geometry and electromagnetic forces. Even so, much of the inflowing material gets ejected before it reaches the event horizon, blown outward by radiation pressure that overcomes even the black hole's gravity at certain distances. You are separated from this radiation prison by 26,000 light-years of interstellar space, a buffer so vast that you experience none of its effects directly. But remember, this prison exists at the gravitational center of everything you know. It's the anchor point of your cosmic motion, the massive core around which the Sun and all its planetary companions orbit, and its existence fundamentally shapes what's possible in the inner galaxy. There are regions of our home galaxy where life cannot exist, where planets cannot support biology, not because of anything local, but because of the monster at the center. We've explored the radiation that makes survival impossible, but radiation is just one of the ways Sagittarius A creates lethal environments. Now we need to examine what happens to the stars themselves, the objects massive enough that you'd think they might resist the black hole's influence. They don't. Chapter 4: Stellar Graveyard. Every few thousand years, a star dies at the hands of Sagittarius A. Not through the normal stellar processes of fusion exhaustion and gravitational collapse, but through violent destruction, torn apart by tidal forces so extreme that the star literally ceases to exist as a coherent object. These events, called tidal disruption events represent some of the most energetic phenomena in astrophysics short of supernovae, and they happen regularly in the environment around supermassive black holes. The physics of tidal disruption is brutally simple. As a star approaches a black hole, gravity pulls harder on the near side than the far side. For a star like the Sun approaching Sgr A, this difference becomes significant at a distance called the tidal disruption radius, roughly 100 million kilometers for our star, about 3/4 of the distance from the Sun to Earth. Inside this radius, the tidal forces exceed the star's own gravity, holding it together. The star stretches, elongates, and eventually rips apart into a stream of gas extending millions of kilometers. But here's what makes tidal disruption particularly horrifying. The star doesn't die instantly. The process takes hours. As the stellar material streams toward the black hole, half of it gains enough energy to be ejected back into space, while the other half remains bound to the black hole and spirals inward. The infalling material forms an accretion disk, friction heating it to temperatures of millions of degrees. The star, which spent billions of years fusing hydrogen into helium in a stable core, suddenly becomes a spiral of superheated plasma, screaming toward oblivion at thousands of kilometers per second. Dr. Jane Liu and colleagues, analyzing archival data from X-ray telescopes, discovered evidence of multiple tidal disruption events in the galactic center's recent past. The X-ray signatures are distinctive, a sudden brightening lasting weeks to months, followed by a power law decay extending over years. Each signature represents a star that no longer exists, its mass either consumed by the black hole or ejected into interstellar space as high-velocity gas. The catalogue of these events is growing as more archival data gets analysed, revealing that Sgr A disrupts stars more frequently than previously thought. The S-cluster stars orbiting closest to Sgr A exist in constant danger of this fate. These stars, with names like S2, S4, S55, and dozens of others catalogued by infrared telescopes, follow elliptical orbits that bring them terrifyingly close to the event horizon. S2's orbit, for example, brings it to within 17 light hours at closest approach, a distance where tidal forces, while not yet disruptive, are beginning to affect the star measurably. Observations show that S2's shape distorts slightly during its closest passage, elongated by gravitational stress, but not all S-cluster stars are so fortunate. Simulations suggest that every few thousand years, one of these stars either collides with another or receives a gravitational perturbation that changes its orbit just enough to send it below the tidal disruption radius. When that happens, the star has no defense. Its own gravity cannot save it. Nuclear fusion cannot protect it. The star simply ceases to be a star and becomes fuel for the black hole's next feeding frenzy. The debris from tidal disruptions doesn't vanish quietly. When a star gets torn apart, its material carries enormous kinetic energy, velocities of thousands of kilometers per second, temperatures high enough to emit X-rays and extreme ultraviolet radiation. This material collides with the existing accretion disk, creating shocks that heat the gas to even higher temperatures. The result is a luminous flare that can briefly outshine the entire galactic center in X-ray wavelengths. These flares announce to the galaxy that Sgr A has fed, that another star has died, that the monster remains active. Dr. Paco Ramos Almeida and his team at the University of La Laguna studied the statistical frequency of tidal disruptions around supermassive black holes and determined that Sgr A likely destroys a star every 10,000 to 100,000 years on average. This might sound infrequent, but remember, we're watching a single black hole over human timescales measured in decades. Over the 4.6 billion year history of the solar system, Sagittarius A has likely consumed between 46,000 and 460,000 stars through tidal disruption alone, nearly 500,000 stellar deaths, each one converting stellar material into either black hole mass or high-velocity ejecta. The galactic center isn't just dangerous, it's actively reducing the stellar population through systematic destruction. Consider the perspective of any planets that might have orbited those disrupted stars. Imagine an Earth-like world, perhaps with life, orbiting a Sun-like star in the galactic center region. For billions of years, this world experiences relative stability. The star provides light and heat, life evolves, perhaps even civilizations arise. Then, due to gravitational interactions with neighboring stars, the orbit shifts slightly. The star begins falling toward Sgr A. Over centuries, the central black hole grows brighter in the sky of this planet. The inhabitants might observe it, with curiosity, tracking its apparent motion, calculating trajectories, and then the tidal forces arrive. First, the star's shape distorts slightly, barely noticeable except to precise instruments, then more dramatically, developing an obvious bulge on the side facing the black hole. The star's surface begins experiencing gravitational stress, triggering increased stellar activity, more flares, unstable fusion. On the planet, temperatures rise, radiation levels spike, the sky, once dominated by a stable star, becomes chaotic with stellar storms. And then, in a period of hours, the star stretches, elongates, and tears apart. The planet, still orbiting, where the star used to be, finds itself suddenly in darkness, plunging through a stream of gas that was formerly its sun. What happens next depends on the planet's specific trajectory. It might get captured by the black hole's gravity, spiraling inward over weeks or months before crossing the event horizon. It might receive enough velocity from the disruption to escape entirely, flung into interstellar space as a rogue planet, carrying the frozen remnants of whatever life existed on its surface. Or it might become part of the debris field, smashed apart by collisions with other ejected material. None of these outcomes preserve anything living. The world dies with its star, another casualty of proximity to Sagittarius A. But tidal disruption isn't the only way Sgr A destroys stars. The environment around the black hole also facilitates stellar collisions at rates far higher than anywhere else in the galaxy. The S-cluster region is extraordinarily dense by cosmic standards, tens of thousands of stars packed into a volume that would contain only a handful of stars in the solar neighborhood. At such densities, with orbital velocities exceeding thousands of kilometers per second, stars occasionally collide with each other. When two stars collide at relativistic velocities, the result isn't a gentle merger. It's an explosion. The kinetic energy of the collision converts into heat, instantly vaporizing the stellar material at the impact point. The stars don't bounce off each other. They interpenetrate, their plasma mixing and exploding outward. The energy released can rival a supernova, sending shockwaves through the surrounding region and potentially triggering additional disruptions in nearby stars. The galactic center experiences these stellar collisions every few 100,000 years, each one adding to the chaotic violence of the environment. Dr. Tal Alexander at the Weizmann Institute of Science has modeled the long-term evolution of the S-cluster and determined that it cannot be stable over timescales of hundreds of millions of years. The gravitational interactions between stars, combined with perturbations from the black hole's influence, inevitably lead to orbital decay for some fraction of the stellar population. This means the S-cluster we observe today is not the same population that existed 1 billion years ago. It's been continuously replenished, either by stars migrating inward from greater distances or by star formation occurring near the black hole itself, replacing the stars that have been destroyed. This creates a disturbing realization. The region immediately around Sgr A is a stellar meat grinder operating over cosmic timescales. Stars venture too close and get destroyed. The black hole consumes some of the material, the rest gets ejected or forms new stars that will eventually suffer the same fate. It's a cycle of creation and destruction, with destruction dominating over long periods. The net effect is that matter gradually falls into the black hole, increasing its mass over billions of years, while the surrounding environment remains, perpetually dangerous to stellar inhabitants. You're witnessing this stellar graveyard from a safe distance, observing through telescopes the fates of stars that died decades or centuries or millennia ago, their light only now reaching Earth after its long journey through interstellar space. Each star in the S cluster that you can see in infrared images is temporary. Each one exists on borrowed time, following an orbit that might last another million years or might decay in the next 100,000. The certainty of their eventual destruction is absolute. The only variable is timing. And this raises an uncomfortable question. If individual stars cannot survive indefinitely near Sagittarius A, what about stellar systems? What about planets, asteroids, comets? All the material that typically orbits stars throughout the galaxy? The answer is that these objects face additional dangers beyond the destruction of their parent stars. The magnetic fields surrounding the black hole create threats that affect even small bodies, twisting and distorting space in ways that make long-term orbital stability impossible. The stellar graveyard around Sgr A isn't just a collection of dead stars. It's an active killing field where the normal rules of stellar evolution break down. Stars don't get to age gracefully, expanding into red giants and shedding their outer layers to form planetary nebulae. They get torn apart violently, their materials scattered or consumed, their planetary systems destroyed, and this process has been ongoing for billions of years, grinding away at the stellar population with patient, unstoppable efficiency. We've seen how Sgr A destroys stars through tidal forces and collisions. But there's another layer to the danger, one that operates at even more fundamental levels. The magnetic fields surrounding the black hole don't just channel radiation, they warp the very structure of space, creating zones where the normal behavior of matter and energy breaks down completely. Chapter 5. Magnetic Chaos. The magnetic field surrounding Sagittarius AE is so powerful that it would rip the iron from your blood. Not metaphorically, literally. At field strengths approaching 1 trillion times Earth's magnetic field, the electromagnetic, forces on charged particles and magnetic materials exceed gravitational forces, chemical bonds, and almost every other force in nature except the strong nuclear force holding atomic nuclei together. In this environment, magnetism doesn't just influence motion, it dominates everything. These fields don't exist in isolation. They're generated by the motion of charged particles in the accretion disk, electrons and ions spiraling around the black hole at substantial fractions of light speed. This creates a dynamo effect similar to Earth's magnetic field generation, but scaled up by factors of trillions. The result is a magnetic field structure that extends from the event horizon outward for light years, creating a vast region where electromagnetic forces shape the flow of matter and energy. Dr. Shepard Doleman, the director of the Event Horizon Telescope project, described these magnetic fields as the puppet strings controlling the black hole's feeding process. Matter falling toward Sgr A doesn't simply spiral inward under gravity alone. The magnetic field lines act like rails, channeling material along specific trajectories. Charged particles follow these field lines with extraordinary precision, spiraling around them in helical paths. This creates structure in the accretion flow, streams of material following magnetic highways toward the event horizon. But here's where the physics becomes truly bizarre. The magnetic fields near a rotating black hole don't just exist in three-dimensional space. They exist in space-time, following the curvature and rotation imposed by the black hole itself. This phenomenon, called frame dragging, means that space itself rotates near the black hole. The magnetic field lines embedded in this rotating space-time get twisted into complex helical structures that rotate along with the space they occupy. The result is a magnetic field geometry that would be impossible anywhere else in the universe. Field lines that loop, twist, and reconnect in ways that violate our intuition about how magnetic fields should behave. Magnetic reconnection events. In this environment, release energy comparable to millions of nuclear weapons detonating simultaneously. When field lines with opposite polarity collide and reconnect, the magnetic energy stored in the field configuration converts into kinetic energy of particles. Electrons and protons get accelerated to velocities approaching light speed in microseconds. The released energy appears as brilliant flares across the electromagnetic spectrum, radio waves, X-rays, gamma rays, all generated in a fraction of a second from a region smaller than Earth's orbit around the Sun. Observations with the Atacama Large Millimeter Submillimeter Array, ALMA, in Chile, have captured evidence of these reconnection events happening in real time around Sgr A. The radio emission from the black hole fluctuates on timescales of minutes, with intensity variations that correlate with theoretical predictions for magnetic reconnection. Each fluctuation represents another violent release of magnetic energy, another burst of particles accelerated to deadly velocities, another injection of high-energy radiation into the surrounding environment. The magnetic field structure also determines where material can and cannot exist stably around the black hole. There's a concept in plasma physics called magnetic pressure, the effective pressure exerted by magnetic fields on charged particles. Near Sgr A, the magnetic pressure in certain regions exceeds the gas pressure by factors of hundreds. This means that gas gets expelled from these regions, unable to exist there regardless of gravitational attraction. The magnetic field literally carves out voids in the accretion flow, creating a Swiss cheese structure of dense filaments separated by near vacuum. These filamentary structures appear in radio observations as long, thin strands of emission extending away from the galactic center. Some stretch for over 100 light-years, perfectly straight, despite crossing regions with turbulent gas dynamics. The only force capable of maintaining such structures over such distances is magnetism. The field lines act like cosmic cables, channeling charged particles along their length and emitting synchrotron radiation as the particles spiral. Each filament represents a magnetic highway stretching from the black hole's immediate vicinity out into the broader galactic center region. Dr. Farhad Yousefzadeh at Northwestern University has spent decades studying these magnetic filaments and discovered something remarkable. They're constantly changing. New filaments appear, existing ones fade or break apart, and the overall pattern evolves on timescales of years. This indicates that the magnetic field around Sgr A is not static. It's dynamic, churning, reconfiguring itself in response to changes in the accretion flow and the black hole's feeding patterns. The environment isn't just magnetically hostile, it's magnetically chaotic. For any object trying to exist in this environment, the implications are severe. Spacecraft electronics would be overwhelmed by electromagnetic interference orders of magnitude beyond anything experienced in Earth's magnetic field. The compass needles wouldn't just point toward magnetic north, they'd spin uncontrollably. As the field direction changed on timescales of seconds, any metallic components would experience forces trying to align them with field lines, creating torques that could tear structures apart. And that's before considering the induced electrical currents from time-varying fields, which would create heating and electrical discharge throughout any conducting material. But the magnetic chaos creates another, more subtle danger. It makes navigation impossible. In normal space, you can determine your position and velocity by observing stars and tracking your motion relative to them. Near Sgr A, the magnetic fields deflect light through the phenomenon of Faraday rotation, polarized light passing through. Magnetized plasma has its polarization angle rotated by an amount depending on the field strength and the density of charged particles. Near the black hole, this rotation can exceed thousands of degrees, completely scrambling the polarization information and distorting the apparent positions of background objects. This means that an observer near Sgr A would see a distorted sky. Stars would appear in slightly wrong positions, their light bent not just by gravitational lensing, but by magnetic refraction. The effect would vary with time as the magnetic field evolved, making it impossible to maintain accurate stellar references. For navigation, you couldn't rely on conventional astronomical techniques to determine where you were or which direction you were moving. The magnetic environment would create a kind of optical chaos in addition to the physical chaos of radiation and tidal forces. The magnetic fields also play a crucial role in generating the jets that we'll explore in detail shortly. But even without jets, the field geometry near Sgr A creates natural accelerators for charged particles. Regions where field lines converge act like magnetic nozzles, focusing particles and accelerating them through electromagnetic forces. These natural particle accelerators achieve energies that rival or exceed the most powerful human-built accelerators like the Large Hadron Collider. The difference is that nature's version operates continuously over volumes measuring light hours across, generating particle beams that would destroy anything in their path. Consider what happens to atoms in this environment. An isolated hydrogen atom consists of a proton nucleus with an electron in orbit around it, bound by electromagnetic attraction. In a magnetic field of normal strength, this configuration remains stable. The binding energy exceeds the magnetic interaction energy by comfortable margins. But in a trillion Tesla magnetic field, the math changes. The magnetic interaction energy becomes comparable to the binding energy. The atom distorts, the electron orbit becomes elongated along the field direction, and at the strongest field strengths, the atom can't exist in its normal configuration at all. Matter itself becomes magnetically stressed at the atomic level. This phenomenon, predicted by quantum mechanics but never observed in Earth laboratories due to our inability to generate such strong fields, likely occurs throughout the region. Near Sgr A, atoms don't behave normally. Chemical bonds become unstable. Materials that would be rigid under normal conditions might flow like liquids under magnetic stress. The fundamental properties of matter that we rely on, hardness, chemical stability, electrical conductivity, all become uncertain in extreme magnetic environments. Dr. Monika Mosztybrodska at Radboud University has created simulations of the magnetized plasma around Sgr A that reveal structures evolving on timescales of minutes. Bright spots appear and disappear, streams of material form and dissipate, and the overall pattern churns like a pot of boiling water, except this is space-time itself churning, dragged along by the rotating black hole and structured by magnetic fields powerful enough to reshape the fundamental behavior of matter. The simulations match observations remarkably well, giving us confidence that we understand the basic physics, but they also reveal just how chaotic and unpredictable the environment truly is. You're separated from this magnetic chaos by 26,000 light-years, and by the fortunate fact that magnetic fields weaken with distance much faster than gravity does. The trillion Tesla fields near the event horizon have dropped to negligible values, by the time their influence reaches the outer galaxy. Earth's magnetic field, generated by our planet's liquid iron core, is weak by astronomical standards but perfectly adequate for protecting us from solar wind and cosmic rays. We're shielded from the magnetic chaos at the galactic center by sheer distance, a buffer that makes life possible. But distance doesn't completely protect us from every manifestation of Sgr A's magnetic influence, because those magnetic fields don't just channel matter into the black hole. Sometimes they channel it away, launching material outward in focused beams that can extend for thousands of light years. And when those beams form, they carry destruction far beyond the immediate vicinity of the black hole. Chapter 6. Galactic. Cannon supermassive black holes don't just consume matter, they also expel it, sometimes with such violence that the ejected material reaches velocities exceeding 99% the speed of light. These outflows, called relativistic jets, represent one of the most energetic phenomena in astrophysics. And while Sagittarius A isn't currently producing strong jets, the evidence suggests it has done so in the past and could do so again in the future. When it does, the black hole effectively becomes a galactic cannon, firing particle beams that can affect regions thousands of light years distant. The mechanism behind jet formation involves the magnetic fields we just explored, but in a specific configuration. When the accretion disk is well fed and the magnetic fields are properly aligned with the black hole's rotational axis, the system can launch material along those field lines rather than funneling everything into the event horizon. Think of it as a cosmic railgun. Charged particles get accelerated along magnetic field lines that extend perpendicular to the accretion disk, reaching extraordinary velocities through electromagnetic forces that dwarf the black hole's gravitational pull at those distances. The physics involved is described by the Blandford-Znajek mechanism, named after Roger Blandford and Roman Znajek, who first proposed it in 1977. The rotating black hole drags space-time around with it, and this frame-dragging effect twists magnetic field lines that thread through the event horizon. The twisted field lines extract rotational energy from the black hole itself, converting it into electromagnetic energy that accelerates particles along the jet axis. It's one of the few processes in nature that can tap directly into a black hole's rotational energy, and that energy reservoir is enormous. A 4 million solar mass black hole, rotating at even moderate speeds, contains rotational energy equivalent to roughly 1 million supernovae. The Blandford-Znajek mechanism can extract a fraction of this energy and channel it into jets over periods of thousands to millions of years. The result is sustained power output that can exceed the total luminosity of all stars in a galaxy combined. Active galactic nuclei powered by jets are among the brightest objects in the universe, visible across billions of light years, specifically because their jets beam energy so efficiently in our direction. Now, Sagittarius A is not currently producing jets at these extreme levels. The black hole is underfed, receiving only sparse material from its surroundings, and the jets it does produce are weak by comparison to objects like M87 Teaks or the quasar 3C273, but weak is relative. Even Sgr A's modest outflows carry enough energy to significantly affect the galactic center environment. Radio observations reveal collimated structures extending several light years from the black hole along axes perpendicular to the accretion disk. These aren't the massive, thousands of light years long jets seen in active galaxies, but they're real, they're measurable, and they demonstrate that the jet mechanism operates at least partially in our galactic center. The danger comes from what happens when Sgr A receives more material to feed on. Simulations by astrophysicist Sean Ressler at the University of California, Santa Barbara show that if the black hole's accretion rate increased by factors of just 10 to 100, the jet power could increase by factors of thousands. The relationship isn't linear, it's superlinear, meaning that modest increases in feeding produce disproportionate increases in jet power. This creates a threshold effect. Below a certain accretion rate, jets are weak and barely noticeable. Above that threshold, they become dominant features capable of affecting the entire galactic center. What would it look like if Sagittarius A formed strong jets? The particle beams would punch through the surrounding gas clouds, heating them to millions of degrees through shockwave interactions. The jets would excavate cavities in the interstellar medium, pushing gas aside and creating bubble structures that could persist for millions of years. X-ray and gamma-ray emission from the jets would flood the galactic center region with high-energy radiation, far exceeding even the already extreme levels we've discussed. And the jets would channel this destruction outward, potentially affecting regions tens of thousands of light-years from the black hole itself. The Fermi bubbles we discussed earlier might be remnants of past jet activity from Sgr A. While some models suggest they formed from a general explosive outflow, other analyses indicate they have the characteristic double-lobed structure expected from jets oriented perpendicular to the galactic disk. If this interpretation is correct, then Sagittarius A produced jets powerful enough to inflate 25,000 light-year bubbles within the last 10 million years. That represents jet power exceeding 10 to 40 ergs per second, roughly equivalent to the luminosity of 100 million suns, sustained over thousands of years. Dr. Jos Bland Hawthorne at the University of Sydney has proposed that these ancient jets might have sterilized the galactic center of any planets capable of supporting life. The radiation levels and particle bombardment from jets powerful enough to create the Fermi bubbles would be lethal across volumes spanning thousands of light years. Any biosphere within that zone would face extinction from high-energy particles, penetrating atmospheres and delivering doses that would destroy even the hardiest extremophile organisms. Life might evolve during the quiet periods between jet episodes, but it would be wiped out repeatedly every few million years when the black hole fed heavily enough to activate the jet mechanism. This creates a model of the galactic center as a permanently hostile environment on cosmological timescales. Even if conditions are merely extreme during quiet periods like the present, they become absolutely lethal during active periods when jets form. Any advanced civilization in the galactic center would need to recognize this danger and either develop technology to survive it or accept periodic extinction events as inevitable. There's no escaping the jets. They fill vast volumes of space, and their effects propagate at light speed, giving no advance warning. The jets also carry another insidious danger. They can trigger star formation in the regions they interact with. When jet material plows into gas clouds, the compression can cause gravitational collapse and the birth of new stars. This sounds beneficial, creating stars rather than destroying them. But remember where those stars are forming: in the galactic center region, near the black hole that will eventually destroy many of them. The jets effectively create stellar populations specifically in the danger zone, seeding the region with stars that exist on borrowed time. It's a cycle of creation and destruction operating over millions of years, with the black hole continuously replenishing the stellar material it consumes. Observations of other galaxies with active supermassive black holes show what happens when jets run at full power. In the galaxy M87, the jet extends for at least 5,000 light-years from the central black hole and can be traced through radio emission out to 50,000 light-years or more. The jet in M87 has enough power to blow bubbles in the surrounding hot gas that are hundreds of thousands of light-years across. Material in the jet moves at 99.5% the speed of light, carrying kinetic energy that exceeds the binding energy of entire star clusters. If Sgr A produced a jet with even 1% of M87's power, it would fundamentally reshape the galactic center environment. The question isn't whether Sagittarius A can produce such jets. The physics is well understood, and we know the mechanism operates. in black holes ranging from stellar mass to billions of solar masses. The question is when? What conditions need to be met for Sgr A to transition from its current quiet state to an active state with powerful jets? The answer likely involves both the accretion rate and the magnetic field configuration. If the black hole receives enough material and the magnetic fields happen to be oriented properly, jets form naturally as a consequence of the system's physics. There's speculation among astronomers that the Milky Way undergoes cycles of activity, with Sgr A spending most of its time in a quiet state, but occasionally flaring into activity for periods of thousands to millions of years. During these active phases, the galaxy would look dramatically different. The core would be bright in X-rays and gamma rays, jets would extend far above and below the galactic plane, and the entire central region would be bathed in radiation, far exceeding the current environment. These active phases might be triggered by major galaxy mergers or by the capture of particularly dense gas clouds that provide sustained fuel for the black hole. We're fortunate to live during a quiet phase, when Sgr A operates as a relatively low-power object, but the potential for it to become a galactic cannon remains embedded in the physics of the system. The magnetic fields are there, the rotation is there. The only missing ingredient is sufficient fuel. And in a galactic environment where clouds wander unpredictably and stellar dynamics can funnel material inward over millions of years, it's only a matter of time before that fuel arrives. You exist in a galaxy that contains at its center a loaded weapon. The weapon is currently on standby, barely ticking over at a fraction of its potential power, but it's loaded, aimed perpendicular to the galactic plane, and fully capable of firing whenever circumstances provide the trigger. The jets of Sagittarius A represent potential danger extending far beyond the immediate galactic center, danger that could manifest on timescales of millennia, or less if conditions change. And if jets represent the black hole's ability to project danger outward, there's an even more fundamental form of danger that operates inward, the distortion of space-time itself. Because near Sagittarius A, the fabric of reality bends so severely that time stops, space becomes infinite, and the very concept of causality breaks down. Chapter 7. Time Distortion. If you could somehow survive close to Sagittarius A and looked at a clock on a spaceship hovering far from the black hole, you'd witness something deeply unsettling. The clock would appear to tick faster, much faster, and the closer you got to the event horizon, the more extreme this effect would become, until at the event horizon itself, an infinite amount of time would appear to pass in the outside universe in a single moment of your subjective time. This is gravitational time dilation, one of Einstein's most profound predictions. And around Sgr A, it reaches extremes that make science fiction seem conservative. The mathematics behind this phenomenon emerges directly from general relativity. Gravity doesn't just pull on matter, it warps space-time itself, and stronger gravitational fields create greater warping. This warping affects the passage of time, making clocks tick at different rates depending on the gravitational field strength they experience. On Earth's surface, a clock runs about 1 second per year slower than an identical clock in orbit, due to our planet's relatively weak gravitational field. Near Sagittarius A, the effect is billions of times more extreme. At a distance of just 10 times the event horizon radius from Sgr A kicks, a clock would run at approximately 30% slower than a clock far from the black hole. This means that for every 10 hours passing in the outside universe, only 3 hours would pass for an observer hovering at that location. Move closer to 5 times the event horizon radius, and time slows to about half normal speed. At twice the radius, still technically outside the event horizon, time crawls at perhaps 10% of normal speed. And at the event horizon itself, time dilation becomes infinite. Time stops completely from the perspective of a distant observer, Dr. Andrea. Gez's team has actually measured this effect using the star S2 during its closest approach to Sgr A. The star's light shows gravitational redshift. The photons lose energy climbing out of the black hole's gravitational well that precisely matches the predictions of general relativity. The amount of redshift corresponds to a time dilation factor of about 0.999 at S2's closest approach, meaning time runs roughly 0.01% slower there than in the outer galaxy. It sounds small, but consider S2 is still at a distance of 17 light hours, far from the event horizon. The fact that we can measure time dilation at such distances demonstrates just how extreme the gravitational field around Sgr A truly is. Now, consider the implications for anything falling toward the black hole. From the perspective of the infalling object, the journey from far away to the event horizon takes a finite amount of time, perhaps a few hours for a trajectory passing near the S-cluster stars. But from the perspective of a distant observer, watching this happen, the object appears to slow down as it approaches the horizon, taking longer and longer to cover each additional millimeter of distance. The light from the object redshifts, dimming and shifting toward longer wavelengths. Eventually, the object appears to freeze at the event horizon, its light so redshifted that it becomes undetectable, while from the object's own perspective, it crosses the horizon and continues falling toward the central singularity in finite time. This creates a bizarre asymmetry in how events unfold. An astronaut falling into Sgr A would experience the passage from event horizon to singularity in perhaps a few thousandths of a second, based on calculations of the tidal forces and the size of the black hole. But an observer, watching from a safe distance, would never see the astronaut cross the horizon at all. They'd see the astronaut approach asymptotically, getting closer and closer, but never quite reaching the boundary, their image redshifted into invisibility over the course of hours or days. Two perspectives on the same event, yielding completely different timelines. Neither perspective is wrong, they're both correct descriptions of reality from different reference frames. But they're irreconcilable. The time dilation near Sgr A also affects how we observe the black hole itself. When we watch matter spiraling in the accretion disk, the material closest to the event horizon appears to slow down from our perspective. This means the accretion disk has an effective inner edge, a region where matter seems to hover, glowing intensely, before finally redshifting away into invisibility. The Event Horizon Telescope images of Sgr A show this effect, a bright ring surrounding a dark center. The ring isn't the event horizon itself, it's the photon sphere where light can theoretically orbit the black hole, and where time dilation becomes so extreme that the entire history of the universe would appear to unfold in moments from the perspective of someone at that location. But time dilation creates dangers beyond the merely observational. It affects causality itself. Near the event horizon, the future light cone, the region of space-time that can be causally affected by events happening now, begins to tilt toward the black hole. Far from the black hole, your future is relatively unconstrained. You can choose to move in any spatial direction, and those paths remain open. But near the event horizon, space-time curves so severely that all future paths lead inward. You cannot hover at a fixed distance. You cannot move sideways or outward. Every possible future involves getting closer to the singularity. Your future has been geometrically constrained by the curvature of space-time itself. This phenomenon, sometimes called the waterfall analogy, compares space-time near a black hole to a river flowing toward a waterfall. Far from the waterfall, you can swim in any direction, upstream, downstream, across the current. As you get closer, the current strengthens, making it harder to swim upstream but still possible. But beyond a certain point, the current exceeds your maximum swimming speed, and downstream becomes inevitable. The event horizon is that point of no return, where space-time flows inward at the speed of light, making escape impossible regardless of how fast you try to move outward. Dr. Kip Thorne, whose work on black hole physics earned him a Nobel Prize, has emphasized that this isn't a limitation of technology or engineering, it's a fundamental property of geometry. Space-time itself provides no paths that lead from inside the event horizon to outside. Those paths don't exist in the same way that paths leading backward in time don't exist. You can't engineer a solution because there's no solution to engineer. The geometry simply doesn't permit it. The extreme time dilation also creates what's called a gravitational time machine effect, though not in the sense of allowing travel to the past. If you could somehow survive close to the event horizon for what felt like a few hours and then escape back to a safe distance, you'd find that thousands or millions of years had passed in the outside universe. You'd have effectively traveled to the future by allowing time dilation to slow your personal clock relative to everyone else's. Science fiction has explored this concept extensively, but near Sgr A, it's not fiction. It's inevitable physics for any object that ventures close and somehow manages to escape. Of course, escaping is the impossible part. The velocities required to maintain position near the event horizon exceed anything achievable with conventional propulsion. Chemical rockets max out at perhaps 5 kilometers per second of delta V with optimistic staging. Ion drives might achieve 50 kilometers per second over long periods. But hovering near Sgr A's event horizon requires velocities approaching 300,000 kilometers per second, the speed of light itself. No material propulsion system can provide such thrust. You'd need to manipulate space-time itself, and we have no technology that can do that at the required scales. This creates yet another layer of the danger surrounding Sagittarius A. It's a place where your future becomes constrained, where your choices narrow to a single option continued infall, and where the passage of time itself becomes a weapon. The time dilation doesn't need to kill you directly. It just needs to slow your clock enough that the universe ages around you until your resources run out, your systems fail, or external events render your survival moot. There's also the psychological dimension to consider. Imagine being part of a mission that ventures close to Sgr A. Not into the black hole, but into the region where time dilation becomes noticeable. You spend what feels like a week conducting observations, gathering data, performing experiments. You return home to find that decades have passed. Everyone you knew has aged or died. The mission you left as part of has been forgotten or become historical trivia. You've been disconnected from your own timeline, thrust into a future you didn't choose simply by venturing into a region where space-time curves too severely. The time distortion around Sagittarius A represents danger at the most fundamental level. Danger to causality, to the flow of time, to the very notion of having a future that remains open to multiple possibilities. It's not dramatic like stellar destruction or violent like radiation exposure. It's quiet, geometric, and absolute. And it operates continuously, eternally, as an inevitable consequence of having 4 million solar masses compressed into a region smaller than Mercury's orbit. You experience time normally, flowing steadily from past to future at a rate of 1 second per second, because you exist in a region of relatively flat space-time. Earth's gravity barely warps the local geometry. The Sun's gravity creates minor perturbations. But at the center of the galaxy, space-time is so warped that time itself becomes elastic, variable, and ultimately frozen at the boundary beyond which nothing returns. We've explored how Sgr A distorts time, but time dilation, while profound, is merely a symptom of the deeper reality. Nothing that crosses the event horizon ever escapes. This isn't a matter of needing more thrust or better technology. It's a fundamental truth about the geometry of space-time near supermassive black holes. And understanding why escape is impossible reveals just how completely dominant these objects are over everything in their vicinity. Chapter 8. Impossible. Escape. The event horizon of Sagittarius A isn't a physical surface. It's a mathematical boundary in space-time marking the point of no return. Cross it, and every path through space and time leads inward toward the singularity at the center. No matter which direction you point your spacecraft, no matter how much thrust you apply, no matter what exotic physics you might attempt to exploit, you cannot escape. This isn't a limitation of current technology. It's not something that a more advanced civilization could solve with better engines or cleverer tactics. It's a fundamental feature of the geometry of space-time itself. To understand why escape is impossible, consider what happens to the structure of space-time inside the event horizon. In normal space, time flows in one direction, from past to future, while you have freedom to move in any of three spatial directions. This is the framework that makes navigation possible, that allows you to choose destinations and plot courses. But inside the event horizon, this relationship inverts. The radial direction toward the singularity becomes time-like, meaning it's no longer a spatial direction you can choose to move along or not. It becomes part of your timeline, as inevitable as aging, asking, can you escape a black hole after crossing the event horizon? Is mathematically equivalent to asking, can you travel backward in time? The answer isn't that we haven't discovered how yet. The answer is that the question requests something that doesn't exist in the structure of reality. There are no world lines, no possible paths through space-time that connect the interior of the event horizon to the exterior. Those connections were severed by the extreme curvature when the black hole formed. Dr. Saul Tucholsky at Cornell University has spent decades calculating the trajectories of particles and light around black holes, and emphasizes that the event horizon represents an absolute boundary. His equations, derived directly from Einstein's field equations of general relativity, show that the escape velocity at the event horizon exactly equals the speed of light. Not 99.9% of light speed, exactly light speed. Since nothing with mass can accelerate to light speed, and since light itself can only travel at light speed without exceeding it, nothing can achieve the velocity required to escape from the event
horizon or anywhere inside it, but it's even worse than that.
The concept of escape velocity assumes you're trying to move away from something. Inside the event horizon, moving away from the singularity isn't even a meaningful concept. Every direction in space, when viewed from inside the horizon, actually points toward the singularity at some point in your future. You could point your spacecraft away from what you think is the singularity and fire your engines at maximum thrust, and you'd still find yourself moving toward it. The geometry permits no other outcome. This creates a deeply disturbing realization. Once you cross the event horizon of Sagittarius A, your death becomes not just probable, but geometrically mandated. The space-time you inhabit no longer contains any paths that lead to continued existence. Every possible future, every decision you could make, every action you could take terminates at the singularity within a few thousandths of a second. You haven't just entered a dangerous region, you've entered a region where the concept of survival has been erased from the structure of space-time itself. The singularity at the center of Sgr A represents another level of impossibility. This is where space-time curvature becomes infinite, where the equations of general relativity break down because they predict infinities that physics cannot interpret. We don't actually know what happens at the singularity because our best theory of gravity fails there. Quantum effects should become important at such extreme conditions, but we don't have a working theory of quantum gravity to tell us what those effects would be. The singularity is a boundary of knowledge itself, a place where our ability to describe reality mathematically simply stops. What we can say is that tidal forces near the singularity become extreme enough to tear apart any object, no matter how strong. The difference in gravitational pull between your head and your feet would exceed the tensile strength of any material, any molecular bond, any atomic structure. You'd be stretched into a stream of particles, a process colorfully termed spaghettification. But even that description might be misleading because at the true singularity, the concepts of particles and material might cease to have meaning. For Sagittarius A, with its 4 million solar mass size, the tidal forces at the event horizon are actually survivable, in the sense that a human body wouldn't be immediately torn apart by the differential gravity at that boundary. The gradient of gravitational force is less extreme for larger black holes than for stellar mass black holes. This creates the bizarre scenario where you could theoretically cross the event horizon alive, intact, and aware of what's happening. You'd have a few thousandths of a second to contemplate your situation before the tidal forces closer to the singularity destroyed you. A few thousandths of a second to realize that your death is now literally written into the geometry of the universe you inhabit. But here's perhaps the most philosophically disturbing aspect of the event horizon. From the perspective of someone watching you fall in, you never cross it. Time dilation means that your image appears to slow down asymptotically, frozen at the boundary, gradually redshifting into invisibility but never actually crossing. From your perspective, you cross the horizon and reach the singularity in finite time. From their perspective, you never cross at all. You simply fade away, your last photons stretched into invisibility over the course of hours or days. This creates a permanent separation in space-time. After you cross the event horizon, there is no future moment at which information about what you experience inside could reach an outside observer. The event horizons creates a causal boundary. Events inside can never affect events outside. Your final moments, whatever they might involve, whatever you might experience in that fraction of a second before reaching the singularity, can never be known to anyone else. That information is removed from the universe, locked away behind a barrier that even light cannot penetrate. Dr. Stephen Hawking famously showed that black holes aren't entirely black. They emit a faint thermal radiation, now called Hawking radiation, generated by quantum effects at the event horizon. This radiation carries away energy, causing black holes to very slowly evaporate over timescales far exceeding the current age of the universe. For Sagittarius A, the evaporation timescale is roughly 10^99 years, a number so large it's essentially meaningless. The universe will die of heat death, protons will decay, all conventional matter will cease to exist, and Sgr A will still be there, barely diminished, continuing to emit its faint quantum glow. But even Hawking radiation doesn't rescue information from inside the event horizon. The radiation is thermal. It carries no information about what fell into the black hole. This creates the black hole information paradox that has troubled theoretical physicists for decades. Quantum mechanics says information cannot be destroyed, but general relativity says that anything crossing the event horizon is lost forever. These two fundamental theories of physics contradict each other when applied to black holes, and despite decades of effort, the contradiction hasn't been fully resolved. For our purposes, the practical implication is clear. Whatever crosses the event horizon of Sagittarius A is gone. Permanently, irrevocably, completely gone from the universe we inhabit. If a star falls in, its matter is removed from the cosmic inventory. If a planet with biosphere falls in, that life is extinguished, in a way more final than any supernova or gamma-ray burst could achieve. The matter doesn't just get destroyed, it gets removed from causally connected space-time entirely. This creates a slow drain on the galaxy's resources. Every time Sgr A consumes something, that mass is effectively deleted from the Milky Way's budget. Over billions of years, this adds up. The black hole has accumulated 4.15 million solar masses through this process, material that was once stars, gas clouds, and possibly planets, now locked away behind an event horizon that permits no returns. And the process continues, slowly and inexorably, reducing the total mass available for star formation and galactic evolution. Consider also what this means for any hypothetical advanced civilization that might exist in the galactic center. They'd need to be constantly vigilant about orbital mechanics, ensuring that nothing important drifted too close to the event horizon. A calculation error, a failed maneuver, an unexpected gravitational perturbation, and whatever was lost would be truly lost, not damaged or destroyed in ways that might permit recovery, but fundamentally removed from reality itself. The black hole would be an ever-present existential threat, a cosmic garbage disposal that accepts input but provides no output. You exist in a universe where most threats, no matter how severe, are theoretically reversible or survivable with sufficient technology. Asteroid impacts can be deflected, radiation can be shielded, even dying stars give billions of years of warning before becoming dangerous. But the event horizon of Sagittarius A represents an absolute threat, one that cannot be defended against once crossed, one that cannot be undone, one that removes you from existence in the most complete way physics allows. And all of this, the time distortion, the impossible escape, the permanent information loss, is happening right now, continuously at the center of our galaxy. Matter is falling in, being processed, and disappearing behind the event horizon. At a rate of about 1,000th of a solar mass per year, it seems like a small amount, but it accumulates. Over the lifetime of the galaxy, Sgr A has consumed millions of solar masses worth of material. Each atom that crosses the horizon is gone forever, added to the black hole's mass, contributing to making it even more dominant and inescapable. The impossibility of escape from Sagittarius A isn't just a practical danger, it's a statement about the limits of what's possible in our universe. There are boundaries that cannot be crossed in reverse. There are decisions that cannot be undone. And there are places where the geometry of space-time itself has become so warped that survival is not merely improbable but geometrically forbidden. But if escape is impossible and individual threats are severe, what happens when we zoom out and consider Sagittarius A not as a local danger, but as a cosmic-scale weapon, because the black hole's true destructive potential operates not just on stars and planets, but on the structure of the galaxy itself. Chapter 9. Ultimate Weapon. Imagine a weapon that could reshape galactic structure, that could sterilize regions spanning thousands of light years, that could prevent star formation across volumes comparable to entire spiral arms, that could fundamentally alter the evolution of galaxies and determine which regions can support life and which cannot. You don't need to imagine it. That weapon exists, and we call it a supermassive black hole. Sagittarius A might be relatively quiet now, but its potential as an instrument of cosmic-scale destruction exceeds anything else in nature. The key to understanding this lies in a concept called feedback. When supermassive black holes actively accrete matter, they don't just consume it quietly. They generate winds, radiation, and jets that heat the surrounding gas, blow it out of the galaxy entirely, or render it too hot to collapse and form stars. This process, called AGN feedback, active galactic nucleus feedback, is now recognized as one of the most important mechanisms shaping galaxy evolution. Black holes don't just respond to their environments, they control them. Dr. Priyamvada Natarajan at Yale University has studied AGN feedback extensively and demonstrated that supermassive black holes regulate the growth of galaxies. Without black hole feedback, galaxies would form far more stars than we observe. The gas would cool, collapse, and continuously form new stellar generations. But when the central black hole activates, the feedback heats the gas to temperatures where gravitational collapse becomes impossible. Star formation shuts down across the entire galaxy. The black hole effectively prevents the galaxy from growing further by destroying the raw material for star formation. For Sagittarius A, operating at current low power, this feedback effect is minimal. The black hole isn't consuming enough material to generate strong feedback. But the evidence of past activity, the Fermi Bubbles, the X-ray echoes, the remnant structures throughout the galactic center, proves that Sgr A has produced powerful feedback in the past. And when it did, the effects were galaxy-wide. The bubbles extend 25,000 light-years above and below the galactic plane, representing regions where hot, shocked gas has been blown out of the disk by explosive energy release from the black hole. Consider what happens during a major feeding event. A dense gas cloud or a cluster of stars falls into Sgr A, suddenly providing a massive influx of material. The accretion rate spikes by factors of thousands. The luminosity increases proportionally. Jets form, channeling energy outward along the rotational axis. Radiation floods the galactic center, and winds, outflows of material accelerated to thousands of kilometers per second, blow outward in all directions. These winds carry enormous kinetic energy, sweeping up gas and dust as they expand. When these winds collide with the surrounding interstellar medium, they create shock waves that heat the gas to millions of degrees. Gas this hot cannot cool and collapse to form stars. It's too energetically excited. The thermal pressure exceeds the gravitational compression needed for star formation. Star formation in the affected region simply stops. Not slowed, not reduced, stopped entirely. And this effect can extend for thousands of light years, affecting volumes that would normally form thousands or millions of stars over hundreds of millions of years. Dr. Elliot Quaterte at Princeton has modeled what would happen if Sagittarius A underwent a major accretion event comparable to those that created the Fermi Bubbles. His simulations show that the energy injection would be sufficient to expel a significant fraction of the gas from the inner few thousand light-years of the galaxy. This gas wouldn't just be heated, it would be accelerated to escape velocity, blown entirely out of the Milky Way into intergalactic space. The galaxy would lose raw material for star formation, becoming less able to form future stellar generations. This might sound like a distant, abstract process, but it has immediate implications for galactic habitability. Star formation doesn't just create stars, it creates the planetary systems where life can potentially arise. If Sgr A undergoes periodic outbursts that suppress star formation in the galactic center for millions of years at a time, then the inner galaxy becomes inhospitable not just to existing life but to the formation of new, life-bearing worlds. The black hole doesn't just destroy the existing civilizations through radiation or tidal forces, it prevents future civilizations from ever arising by suppressing the star formation that would create their homeworlds. The timescales involved are crucial. A single major outburst from Sgr A might last a few thousand to a few million years, short in cosmic terms but long enough to affect multiple generations of star formation. During this period, the galactic center would be an actively hostile environment. After the outburst ends and the black hole returns to quiescence, it takes additional time for the gas to cool, settle back into the galactic disk, and resume forming stars. The total affected period could span tens of millions of years. Life that existed before the outburst would face extinction. Life that might have formed during the outburst can't develop because star formation is suppressed. The black hole creates dead zones in time as well as space, but there's an even more extreme possibility. What if Sagittarius A formed sustained, powerful jets comparable to those in active galaxies? The galaxy M87, whose central black hole we've mentioned, produces jets that extend for thousands of light years and carry power equivalent to billions of suns. Those jets excavate enormous cavities in the surrounding gas, preventing star formation across regions larger than the Milky Way's entire stellar disk. If Sgr A formed similar jets, the impact on our galaxy would be catastrophic on evolutionary timescales. The jets wouldn't directly destroy the Sun or Earth. We're too far from the galactic center and too far off the jet axis. But they would fundamentally alter the galactic environment. The jets would inject energy into the halo of hot gas surrounding the Milky Way, heating it and potentially preventing it from cooling and falling back into the disk. This would shut down the supply of raw material for future star formation throughout the galaxy, not just near the center. Over hundreds of millions of years, the Milky Way would gradually exhaust its available gas, forming fewer and fewer stars, eventually becoming a red and dead galaxy dominated by old, low-mass stars with no new stellar generations replacing them. This scenario might sound like speculation, but observations of other galaxies show it's not only possible, it's common. Many massive elliptical galaxies show evidence of having their star formation shut down by black hole feedback. They contain supermassive black holes that underwent periods of intense activity, generating enough feedback to expel or heat the gas reservoirs, permanently ending significant star formation. These galaxies are graveyards, collections of aging stars with no young populations, slowly fading as their stellar inhabitants exhaust their fuel and die. The Milky Way hasn't suffered this fate, which tells us that Sagittarius A has never undergone sustained feedback powerful enough to permanently suppress star formation. But the potential exists. The physics governing Sgr A is identical to the physics governing the active black holes that killed their host galaxies. The only difference is feeding rate and duration. Give Sgr A enough material for a long enough time, and it could transform the Milky Way from a living star-forming spiral galaxy into a sterile collection of dying stars. Dr. Avi Loeb at Harvard has explored the implications of living in a galaxy with an active, supermassive black hole. His calculations suggest that intelligent life might be impossible in galaxies with highly active black holes because the feedback effects create environments incompatible with long-term biological evolution. Planets might form during quiet periods, but periodic outbursts sterilize them before complex life can develop. Or star formation might be so suppressed that second and third generation stellar systems, the ones rich in heavy elements, necessary for rocky planets and biochemistry, never form in significant numbers. This creates a sobering thought. The reason we exist, the reason Earth developed life and that life evolved into intelligence, might be directly connected to Sagittarius.
A being relatively inactive, we're not just fortunate to live far from the galactic center. We're fortunate to live in a galaxy whose central black hole happens to be underfed, operating at a tiny fraction of its destructive potential.
If Sgr A were more active, the Milky Way might be a very different place, perhaps a place where Earth never formed, or formed but never developed life because the galactic environment was too hostile. You are the descendant of billions of years.
Of cosmic evolution that only occurred because the weapon at the center of your galaxy remained mostly dormant.
The black hole that could reshape entire galactic structures, that could suppress star formation across thousands of light years, that could render vast regions uninhabitable for millions of years, that weapon has been largely inactive throughout Earth's history. We've benefited from living during a cosmic ceasefire. But ceasefires can end. The weapon remains loaded, operational, and fully capable of activating if circumstances change. And when we look at other galaxies, we see that circumstances do change. Black holes do feed. Feedback does activate. Galaxies do get transformed by their central monsters. There's no reason to think the Milky Way is permanently exempt from this process. We're simply in a quiet phase, a phase that might end in thousands of years or millions or billions. The uncertainty doesn't eliminate the danger, it just makes it unpredictable. So we've established that Sagittarius A possesses destructive capabilities extending from individual stars to galaxy-wide scales. But there's one final question we need to address. What would it take to activate this sleeping giant? What might cause Sgr A to transition from its current quiet state to the kind of violent activity we see in other galaxies? Because understanding the trigger mechanisms tells us just how stable or unstable our current cosmic situation really is. Chapter 10. Sleeping Giant. The most terrifying aspect of Sagittarius A isn't what it's doing now, it's what it could do if it woke up. Right now, the black hole operates at perhaps 0.01% of its theoretical maximum power output, feeding on sparse gas trickling inward from the surrounding interstellar medium. But astrophysicists have identified several scenarios that could dramatically increase its feeding rate, transforming it from a quiet monster into an active galactic nucleus, one of the most luminous categories of objects in the entire universe. The most straightforward trigger is a major galaxy merger. When two galaxies collide, their gas reservoirs get funneled toward the centers through gravitational torques. The orderly orbits that kept material at safe distances break down. Massive amounts of gas, potentially billions of solar masses, rain down onto the central black holes of both galaxies. If the Milky Way were to merge with another large galaxy like Andromeda, which is currently on a collision course with us and will arrive in about 4.5 billion years, the resulting merger could wake both Sgr A and Andromeda's central black hole simultaneously. Dr. Lars Hernquist at Harvard has simulated galaxy mergers extensively and shown that they trigger extraordinary black hole activity. During the merger, the central black holes can temporarily shine with luminosities exceeding entire galaxies, billions of times brighter than they were before. This activity lasts for millions to tens of millions of years, flooding the merger, remnant with radiation, generating powerful winds and jets, and fundamentally restructuring the gas distribution throughout the newly merged system. Any life in either galaxy would face an extinction-level radiation environment that persists far longer than any terrestrial extinction event. But galaxy mergers aren't the only trigger mechanism. Even without mergers, massive gas clouds occasionally fall into the galactic center through a combination of random motion and gravitational perturbations. The cloud designated G2, which made a close pass by Sgr A in 2014, was suspected of potentially triggering increased activity. While G2 survived the encounter, likely because it was actually a dust-shrouded star rather than a pure gas cloud, the incident demonstrated that material does venture close to the black hole on regular timescales. A truly massive gas cloud, perhaps several thousand solar masses compressed into a relatively small volume, falling directly into Sgr A could trigger a feeding event lasting thousands of years. The increased accretion would heat the accretion disk, increasing luminosity across all wavelengths. X-ray and gamma-ray flux throughout the galactic center would spike by factors of hundreds or thousands. The radiation environment would become lethal across regions spanning hundreds of light years. And if the accretion rate and magnetic field configuration aligned properly, jets might form, extending the danger zone to thousands of light years. There's also the possibility of stellar cluster infall. The galactic center contains numerous star clusters, gravitationally bound collections of hundreds or thousands of stars. If one of these clusters were perturbed onto a trajectory that brought it close to Sgr A, the black hole would begin disrupting its structure, stripping away stars and funneling them toward the event horizon. This would provide sustained feeding over timescales of thousands to millions of years as the cluster was gradually consumed. The result would be an extended period of elevated activity, far longer than what a single gas cloud infall could produce. Dr. Ron Millard at MIT has studied X-ray binaries, stellar mass black holes actively feeding on companion stars, and notes that they undergo cyclic behavior. They transition between quiescent states with minimal activity and outburst states where luminosity increases by factors of millions. The physics governing these transitions applies to supermassive black holes as well, just on much larger scales. If stellar mass black holes can suddenly activate, so can supermassive ones. Sagittarius A is, in this sense, a time bomb with an uncertain timer. It might remain quiet for another billion years, or it might activate within the next 1,000. The implications of an awakening are profound. Consider what happens to the galactic center environment when Sgr A increases its luminosity by a factor of 1,000,000, a relatively modest increase compared to the most active galactic nuclei. The radiation output would flood the inner galaxy with X-rays and gamma rays at levels that would sterilize any planets within several thousand light years. Molecular clouds would be heated and dissociated, preventing star formation. Existing stars would experience increased stellar winds as their outer atmospheres absorbed energy from the black hole's radiation. And the magnetic field structure would become even more complex and violent, creating zones where particle acceleration reached even more extreme energies. For any civilization in the galactic center, an awakening of Sgr A would be an apocalyptic event. There would be no defense against galaxy-wide radiation increases. Shielding might protect against the initial surge, but sustained exposure over thousands of years would overwhelm any protective measures. The only survival strategy would be evacuation, leaving the galactic center entirely and migrating to regions far enough from Sgr A that the radiation attenuated to survivable levels. But this assumes the civilization had sufficient warning and transportation capability. A sudden activation might give no time for escape. We've been fortunate that Sagittarius A has remained quiet throughout human history, and indeed throughout the entire history of complex life on Earth. The black hole has been feeding at minimal rates for at least the past few million years, the time period during which human ancestors evolved. If Sgr A had undergone a major activation event during the Pleistocene, we wouldn't exist to observe it. Not because Earth would have been directly threatened, we're far too distant for that, but because the galactic environment our solar system formed in might have been different, affecting the processes that led to Earth's habitability. There's an anthropic principle argument lurking here. We observe Sgr A to be quiet because civilizations only arise in galaxies where the central black hole remains quiet long enough for complex life to evolve. Galaxies with highly active black holes might be sterile, their central regions too radiation flooded, and their star formation too suppressed to produce the generations of stellar systems necessary for life. We exist in the Milky Way, specifically, because Sagittarius A has been asleep, and we're capable of studying it specifically because we evolved during a prolonged quiet period. But the future remains uncertain. The Andromeda collision, scheduled to occur in 4.5 billion years, will almost certainly trigger increased activity in Sgr A. By that point, the Sun will be approaching the end of its main sequence lifetime anyway. Earth will likely be uninhabitable. from solar evolution before galactic merger effects become relevant. But the principle remains: major disruptions to galactic dynamics can wake sleeping black holes, and once awakened, they reshape their environments with violence that dwarfs anything terrestrial life has experienced. Dr. Mitchell Begelman at the University of Colorado emphasizes that we're still learning what determines whether a supermassive black hole is active or quiescent. The physics is complex, involving not just the feeding rate, but the magnetic field configuration, the angular momentum of infalling material, and the feedback effects from previous accretion episodes. Small changes in any of these parameters could potentially trigger transitions between states. Sagittarius A might be more fragile, more prone to sudden activation than we currently understand. This is why continued observation of Sgr A is crucial. Every flare we detect, every fluctuation in luminosity, every change in the magnetic field structure teaches us something about how close the black hole is to transitioning to a more active state. The monitoring programs conducted by astronomers worldwide aren't just academic exercises, they're reconnaissance missions, watching a potential threat to ensure it remains dormant. We're keeping an eye on the weapon at the center of our galaxies. You go about your life. Remember that you exist in a cosmic environment shaped by the dormancy of Sagittarius A. The galaxy you inhabit, with its spiral arms rich in young stars and its interstellar medium capable of forming new stellar generations, exists in this form because the central black hole isn't actively destroying it. The structure that cradles our solar system, that provides the heavy elements Earth is made from, that allows star formation in regions like the Orion Nebula, where new planetary systems are born, all of this depends on Sgr A remaining mostly asleep. The sleeping giant at the center of our galaxy is dangerous not just because of what it does, but because of what it could do. The potential for destruction exceeds the current reality by factors of millions. And while we can study the physics, model the scenarios, and monitor the black hole for signs of awakening, we cannot control it. We cannot negotiate with it. We cannot shut it down or disarm it. Sagittarius A is a force of nature operating at scales that reduce human concerns to insignificance. But perhaps there's a strange comfort in that perspective. The black hole that could destroy galactic environments operates by physical laws we understand. It's not malevolent. It's not targeting anything specifically. It simply exists, following the mathematics of general relativity and plasma physics. And in doing so, it creates a hierarchy of cosmic dangers that puts terrestrial threats in perspective. Wars, climate change, asteroid impacts. These are real dangers requiring real solutions. But they pale in comparison to living in a galaxy whose central anchor point is a 4 million solar mass engine of destruction. Throughout this journey into the heart of darkness, we've discovered that Sagittarius A is far more dangerous than simple descriptions of supermassive black hole at galactic center suggest. We've explored the hidden monster lurking beneath dusty obscuration, consuming 4 million solar masses worth of space-time itself. We've examined the violent past written in gamma-ray bubbles and X-ray echoes, proving this monster feeds in catastrophic bursts. We've ventured into the radiation prison where survival is measured in seconds and where the electromagnetic spectrum itself becomes a weapon. We've witnessed the stellar graveyard where stars are torn apart by tidal forces and consumed in hours-long death spirals that release more energy than billions of years of normal fusion. We've confronted the magnetic chaos that warps field lines into twisted geometries impossible anywhere else in nature. We've stared down the galactic cannon capable of projecting destruction across thousands of light years through relativistic jets. We've grappled with time distortion so extreme that time itself stops at the event horizon, creating a boundary where the future collapses into a singularity. We've understood why escape is impossible, not difficult, not technologically challenging, but geometrically forbidden by the structure of space-time. We've recognized the ultimate weapon potential, the ability to suppress star formation and reshape galactic evolution across cosmic timescales. And we've contemplated the sleeping giant scenario, wondering what might trigger the transition from dormancy to catastrophic activity. But perhaps the most profound insight isn't any single danger we've explored. It's the recognition that Sagittarius A operates as a hierarchy of threats extending from subatomic scales to galactic scales. Atoms are disrupted by trillion Tesla magnetic fields. Molecules are dissociated by radiation. Cells are destroyed by particle bombardment. Organisms die within seconds. Stars are torn apart over hours. Star formation is suppressed across millions of years. Entire galaxies are reshaped over billions of years. The black hole connects the smallest scales of physics to the largest scales of astronomy through a continuous chain of destructive processes. As you go about your day after watching this, carry with you the knowledge that you orbit this object. Every second, you and Earth and the Sun move at 230 kilometers per second in a vast ellipse around the galactic center. That orbit takes 230 million years to complete, meaning that when the Sun last occupied its current position in the galaxy, dinosaurs were just beginning their reign on Earth. You're on a cosmic journey circling Sagittarius A, and you always have been. The difference is that now you understand what sits at the center of that journey. When you look up at the night sky toward the constellation Sagittarius, remember that you're looking toward the most extreme environment in the Milky Way. Hidden, behind dust clouds invisible to your eyes, the monster waits. It's not waiting for anything specifically, it simply exists, following the mathematics of general relativity with perfect precision. But its existence shapes your reality more than any terrestrial feature. The galaxy you inhabit has been sculpted by Sgr A's gravity over billions of years. The elements in your body were created in stars that orbited this black hole for millions of years before dying and enriching the interstellar medium with heavy elements. Your entire existence traces back to processes that occurred in the gravitational well of Sagittarius A. You are not separate from the cosmic violence we've explored tonight. You are a product of it, a downstream consequence of galaxy formation that required a supermassive black hole to anchor the structure. The danger posed by Sgr A isn't external to you, it's the context within which your existence became possible. The black hole that could destroy galactic environments is the same black hole that created the stable galactic structure necessary for long-term stellar evolution, heavy element production, and ultimately, life. This creates a profound paradox. The most dangerous object in our galaxy is also the most necessary. Without Sgr A, the Milky Way would be a very different place. Perhaps a loosely bound collection of stars without clear structure. Perhaps a galaxy that never retained enough gas to form later stellar generations. Perhaps something that couldn't support the long-term stability necessary for planets to develop complex biospheres. The danger and the necessity are inseparable. You exist because of Sagittarius A key, and you're endangered by it. Both statements are true simultaneously. If you made it this far through this exploration of cosmic horror and wonder, subscribe and hit the thumbs up button. Check out my video on what happens when galaxies collide. I'm sure you'll love it, especially now that you understand what happens to the supermassive black holes at their centers. That collision, scheduled for 4.5 billion years from now, will wake Sagittarius A from its slumber and transform our galaxy into something we can barely imagine. The black hole at the center of our galaxy is dangerous because it warps space-time to breaking points, because it generates radiation that sterilizes regions spanning thousands of light years, because it destroys stars with casual efficiency, Because it creates magnetic field environments where matter itself behaves strangely, because it can project destruction through jets extending across galactic scales. Because it distorts time until the past and future become indistinguishable, because escape from its gravity is geometrically impossible, because it possesses the potential to reshape entire galaxies through feedback effects, and because we cannot predict when it might transition from sleeping to waking. But it's dangerous, ultimately, because it exists. 4 million solar masses compressed into a region smaller than Mercury's orbit, sitting at the gravitational heart of everything we know, patient and eternal and absolute. Right now, at the
exact center of our galaxy, something is waiting in the darkness. We thought it was sleeping, dormant, perhaps even safe. We were wrong. It's simply resting between meals.